Okay, let's dive right into this. Whether you're trying to build a spam filter, analyze customer feedback, or categorize a massive library of documents, text classification is absolutely the fundamental capability you need. So in this explainer, we're going to break down a really fantastic step-by-step blueprint straight from Google for developers on how to solve text classification problems using machine learning.
It's a pretty great question, right? How do machines actually make sense of our words? Well, to turn the utter chaos of unstructured text into clean, organized data, we need a machine learning classifier. And today, we're actually going to build one from the ground up. But we aren't just going to throw raw data at an algorithm and cross our fingers. No way. We're going to follow a highly structured, battle-tested workflow to get it right. To do that, we'll follow this specific 5-step agenda. We'll start with the foundation of data, look at the SW ratio rule, build the model, train your network, and finally, tune the hyperparameters. Starting with step 1, the foundation of data. As the saying goes, your model is really only as good as its dataset. Gathering high-quality data is quite literally the most important step here, because a supervised machine learning model is entirely dependent on what it's built from. We're going to use a classic example for this, the IMDb movie review dataset. It's a perfect sentiment analysis problem. The goal is super simple. We feed the model a written movie review, and we want it to accurately predict whether the sentiment is positive or negative. Now, there are 4 golden rules of data collection you need to know, and honestly, following these will save your model from failing before you even write a single line of code. First, if you're pulling data from a public API, say X or the New York Times, you've got to watch out for those query rate limits. Second, maximize your training examples. The more data, the better your model will generalize. Third, you absolutely must ensure comparable samples per class to avoid imbalance. You can't have 10,000 positive reviews and only 50 negative ones, or your model is just going to be totally biased. And lastly, make sure your data covers the entire space of possible inputs, all the weird edge case ways people might express their opinions online. Moving on to step 2, the SW ratio rule. This is really the master key to deciding your model architecture.
This is where Google's guidance gets incredibly practical. The S-word ratio is just the number of samples divided by the average number of words per sample in your dataset. That's it. It sounds fancy, but it's just total samples divided by words per sample. And this one single calculation is going to dictate the entire path forward for your model.
So why does this matter? Well, if that ratio is low, specifically under 15,000, you're going to want to use an n-gram model. N-gram models process tokens independently. They don't care about the order of the words, which makes them incredibly efficient for smaller ratios. But if you have a massive dataset and a really high ratio, a sequence model is for sure the way to go. Sequence models actually learn from the adjacency and order of the tokens, so they understand how words relate to each other in a sentence. All right, step 3, building the model. This is where we start assembling the layers, kind of like Lego bricks.
With our data ready and our model type locked in based on that SW ratio, we jump into the construction phase using the TensorFlow Keras API. Building a sequential model really is like snapping together Lego bricks. You stack data processing layers linearly. So the text comes into the input layer, it gets processed in the intermediate layers, depending on your n-gram or sequence choice, and then that last layer spits out your final probability score.
Now let's talk about that very last Lego brick, because it depends entirely on what you're trying to sort. If you're doing binary classification, like our IMDb positive or negative example, you just needed to output one score. For that, you use a sigmoid activation function. It basically says, hey, I'm 85% confident this is a positive review. But if you're doing multi-classification, say sorting news articles into sports, politics, and entertainment, it needs to output one score per class. And for that, you'd use a softmax activation function.
So, if your SW ratio told you to build an n-gram model, what exactly should you build? The clear winner here is a simple 2-layer MLP, or multi-layer perceptron. They are beautifully simple to define, they require very little computation, and they easily beat out other options like gradient boosting or support vector machines for these types of datasets.
On the flip side, what if you're building a sequence model? Well, you can actually give your model a massive head start using pre-trained embeddings. Think of it like handing your model a dictionary before asking it to read a book, so it doesn't have to learn the English language completely from scratch. You can take dense vectors, like glove, which was trained on huge amounts of Wikipedia data, and drop them right into your model's first layer to teach it complex word relationships instantly. And the architectural winner for sequence models? It's the depth-wise separable CNN, or sepCNN. Standard recurrent neural networks are super popular, but they're incredibly computationally heavy.
The sepCNN is way more data efficient and compute efficient, making it the absolute best foundational workhorse for your sequence model build.
Okay, step 4, training your network. It is time to start the engine and minimize those errors.
Training is basically just the machine making a prediction, calculating how wrong it was, and updating its internal weights until it gets it right. To guide this, you pass a few specific parameters to the compile method in Keras. You'll set your metric to accuracy, pick the right loss function based on if you're doing binary or multi-class, and then you choose an optimizer.
Let's be real. Terms like atom optimizer sound super intimidating, but don't let it scare you. It's literally just the mechanic under the hood. It's a mathematical function that looks at the errors identified by the loss function and decides exactly how to tweak the network's weights so it's a little less wrong on the very next try.
The training process itself is a really fascinating loop. You pass in a batch of samples, say 512 reviews at a time, it computes the loss and updates the weights once per batch. Once it's seen the entire training dataset, that is one epoch. But here's the pro move. You use something called early stopping. If the model's accuracy stabilizes and it flatlines after a few epochs, early stopping steps in and stops the training. This saves massive amounts of computing power and keeps the model from just memorizing the data.
Finally, step 5. Tuning the hyperparameters. This is where we tweak the dials for absolute peak performance.
Because every problem is unique, those initial choices we made were just a starting point. Now we've got to fine-tune things. Adjusting the layers controls the complexity of your network. Google found the sweet spots are typically 2 layers for an MLP and 4 layers for a sepCNN, using 32 or 64 units per layer. You'll also want to start your learning rate low, around 1e-4, and adjust it, which controls how drastically the weights swing while it's learning.
Now take a look at this number range, 0.2 to 0.5. This represents the optimal dropout rate for your network. And I know it might sound strange, but one of the absolute best ways to improve your neural network is to actively sabotage it.
Yes, seriously. We use dropout regularization to intentionally drop fractions of the input data. By randomly turning off 20 to 50% of the network's connections during training, the model can't just rely on one single node to recognize a positive review. It forces the whole network to actually generalize and learn robust patterns instead of just memorizing the training set. And if you went the sequence model route, there are 2 specific sepCNN dials to polish up at the end. You'll want to try kernel sizes of 3 or 5, which determines the window of words the model looks at all at once. And keep your embedding dimensions between 50 and 300. This ensures your word vectors hold enough meaning, but aren't so massive that they completely bog down your compute power.
And there you have it. A swift, step-by-step blueprint straight from Google. We've covered everything from analyzing your SWOT ratio to assembling Keras layers, right down to tweaking the dropout rate. The foundation is officially set, and you are ready to build. So, the only question left is, what unstructured chaos are you going to conquer first?